Hello, everyone, and welcome to today's webinar, Successfully Automating Your Welding Process with Robotics, sponsored by OTC DAIHEN. We'll begin in a few minutes. Looks like we still have people joining, so we'll wait a minute for everybody to get on. Okay, well, it looks like we have everyone here. Again, welcome to today's webinar, Successfully Automating Your Welding Process with Robotics, sponsored by OTC DAIHEN. Before I introduce our speaker, if you're having any technical difficulties, please use our chat feature of the webinar so our support team can assist you. Also, you may submit any questions you have throughout the webinar on the side panel on your screen. We'll have a question and answer session at the very end of our webinar. At the end of the webinar, you'll also see a survey appear. Please complete the survey as your feedback is greatly appreciated. Now, on to our webinar. We're very excited to welcome Brian Peoples with us today. Across his 30+ years of experience in the metal fabrication industry, Brian now serves as Regional Sales Manager for OTC DAIHEN, where he has built upon his reputation by helping his customers deliver productivity through the implementation of simple welding and automation solutions. Please join me in welcoming Brian Peoples.
Thanks, Brent. So the presentation I'm going to go over today is going to start out by talking about some of the benefits of robotically automating your welding processes, and then we're going to move on to concerns, issues, things that you should take into consideration to make sure that your new welding cell is welding parts and not sitting in the basement as your treadmill might have been before this COVID stuff began. Sorry, slight technical issue here. So most of the benefits of robotic arc welding come from increased productivity and reduced production costs. Arc on time is dramatically increased with robotic welding. Typically, manual arc on efficiencies are 5 to 20%. So that means your welder is actually pulling the trigger 5 to 20% of the time, depending on the application. If it's a lot of short welds, it tends to be on the lower end of that. A lot of longer welds, it tends to be on the higher end. With robotic applications, those efficiencies usually increase to 60 to 85%. Big part of the reason for that is reduced air cut times, arc air cut times. Robots can move from one location to another location very quickly. They can reposition. They don't have to lift their hoods. So there's a lot of benefit from that. That helps to greatly reduce cycle time. Robots can also weld faster at faster welding speeds oftentimes. Your welding application is the only limit to welding speed. That really doesn't change with robotics, but because robots can go at fast controlled speeds, oftentimes you can approach speed limits that you couldn't attain otherwise. And most welding speeds and deposition rates do increase substantially. You can reduce or eliminate scrap parts with robotic welding. Robots' repeatability ensures weld consistency on each part, on each weld, every time. One of the things that most people don't consider in welding operations is the amount of wire used is directly related to the size of your weld. If you have a weld spec that calls out for a 1/4 inch weld fillet, and your welder is welding to a 5/16 fillet weld, it looks almost the same without pulling a ruler out and really checking it. But a 5/16 inch fillet will require 56.6% more wire and time and gas than it would to do the job that the spec called out. So the converse of that is true as well. If we're calling out for a 1/4 inch fillet weld, the robot can produce that every single time. You're never going to weld under a 1/4 inch, which could cause weld failures, which could be catastrophic depending on what your industry is. Robotic welding can also require less gas. You may be able to do a process change that enables you to use a less expensive gas completely by eliminating helium or even going to CO2 for some applications. But in any case, the gas use can be lowered because travel speeds can be faster, and robots don't get hot and need to blow fans on them. One of the things that happens typically in fabrication shops is the welders are wearing protective gear, PPE, which we're all so familiar with these days, and it's can be a hot and uncomfortable way to spend your day. Welders have fans on them, and oftentimes will increase gas flow beyond what's required for the application, just so they're not blowing the gas away from the job. And electronic gas modules can be added as well if that's necessary to really maximize that. With robots, we typically have much extended consumable lives because there's this consistent stick out with the torch angles are maintained, the wire speed feed, all those things are consistent. That typically increases contact life dramatically. And nozzles are cleaned automatically, and you've got nobody banging on them to get stuff out of them or using them as a hammer to chip slag off of a part. So nozzles typically last exponentially longer than they would in a manual application. With a robot, we have reduced and controlled heat input. So we're minimizing part deformation by putting less heat into the part, oftentimes by welding at faster speeds, but you can also jump from one spot to another spot. So if you had several tacks, or if you're welding a part that's prone to deformation because of the heat you're putting in, you can jump around from one area to another with the robot without repositioning quickly. Also, the whatever deformation that there is because of heat is going to happen the same every time, because it's going to take the robot the same amount of time to do the welds in a given order. So whatever metallurgical deformation you're having is going to be consistent. So oftentimes it can be planned for. You might open up a fixture a little bit to let the material draw your parts into spec. That can be done consistently with robotic welding, a lot easier than manual welding. Also, we can weld closer to part edges on heat sensitive parts without worrying about the weld kind of rolling over and destroying a part or causing rework. In addition to the productivity and cost benefits of a robot, safety is also a major concern. It takes the operator out of the exposure to the hazardous environments. They're away from the arc flash, heat, and the harmful gases that can be given off in a welding plume. Also, an operator is typically away from the robot, loading a part into onto a table or into some tooling. That can be looked at completely differently ergonomically. You don't have to climb around, reach, bend, twist around parts oftentimes. So that really can help with operator comfort and safety overall. Operators are also removed from the proximity if you have a part that requires a lot of heat preheating, or a part that has so much weld on it that the welding environment itself gets to a really high level. The operator can be away from that heat and not exposed to that directly. And another key of robotic welding is really welding clean. If we minimize spatter, if we get prettier looking welds, we're minimizing spatter, that's going to reduce the amount of time that we need to grind or polish things afterwards. Oftentimes, grinding can take more time, more labor than welding the parts does by multiple factors. And that also reduces rejected parts, which can save you from having to do entire batches of parts again. So with the robot, we have improved product quality, not only in appearance, but weld integrity. So our weld strengths are going to be consistent. We're going to have nice, reliable, repeatable welds because of the consistent travel speed and torch angles. Because all of that is consistent, that typically leads to a much better looking weld and a much stronger weld. And your welding power support source also influences weld appearance and strength and what processes you can run. Oftentimes, if you're getting a robot, you can put a higher technology welding power supply on that system that gives you more capability than would typically be used by your manual welding staff. I'm going to turn things over to Brent here for a second for our first poll question.
All right, poll question number 1. What do you consider to be the #1 benefit of robotic welding? Repeatable and consistent weld quality, cycle time reduction, productivity improvement, labor cost savings, ability to grow or maintain business in uncertain times, augment manual welding, free welders for high value work. We'll give everybody 30 seconds to answer the poll question. All right, last call. All right, let's take a look at the results. So it looks like the leader of the answers was repeatable and consistent weld quality. Pretty interesting. I seem to hear that a lot with a lot of customers. I'm sure you do too, Brian.
Absolutely. So in weld quality and consistency, that is there are definitely amazing increases in quality capable from a robot. You never have a robot that's unhappy, or they're never in jail, they're never unhappy, they're never mad at their spouse. So things are consistent not only on a weld-to-weld basis, but throughout the day. They don't get tired at the end of the day or after lunch. So there are a lot of advantages that way as well.
Yeah, and if there's sorry, Brian, but I was gonna say if there's a cleanup process too, that gets consistent. So you can, in a lot of cases, reduce or eliminate that, but whatever that would require gets consistent, and that also down the line, stays consistent throughout the process. So you're not wasting a lot of time there too.
Yeah.
All right, well, I'll kick it back over to Brian.
Thanks, Brent. So at this point, you've realized that there are benefits of robotic welding and you want to automate your welding process. So now we go over into cautions, considerations. How do we make this process successful and make sure we don't end up spending money that's not going to pay back our organization? So the first thing I want to look at, or the first thing I typically look at, is which parts and jobs should we automate? It is, I'll say, relatively common for me to come into a fabrication facility where somebody has a job, a process that they want to automate. And as I'm walking to that job, I see numerous other applications that are very well suited to robotic automation. And then I get to the specific job that they are looking at automating, and maybe it is just difficulty to fixture or difficulty in flexibility. There may be some reason that's probably not going to be the best job. Most things fall into a couple of categories that are automatable. The one thing that I'll say most people think about is if you've got high volume and repeatable jobs, that makes sense for automating. Everybody knows that. You have pallets of parts that you run on a regular basis, small, simple things that you're doing millions of. One of the things that I've been most surprised about in this industry is how many job shops, how many companies that are not running millions or even hundreds of thousands of anything ever are really successful with robots. In that case, there are a lot of things there are a lot of things if you're a job shop that, as I talk through this presentation, that should be helpful for you. One thing is if your parts are laser cut, or if you have a good high tolerance plasma cutter, or if you can slot and tab your parts for easy fixturing, automating with robots is going to be a lot easier, a lot simpler. It doesn't mean that you can't without it. You have to look at the individual jobs. If you have jobs with a lot of weld time, and weld time can be a lot of arc time, a lot of hours, or maybe like cladding jobs, or they can be jobs with stitch welds where an operator has to keep repositioning, jobs that take a lot of time to do. Those often can be simply programmed, easy jobs to automate. This video I'm showing for a couple of reasons. It shows kind of a typical cell, robots welding on one side while an operator is loading the other side. This video also shows a couple things that are a little unique. The tooling on the left side is a modular tooling. The tooling on the right is a more simple clamp type fixturing. So it shows a couple of different ways that you can fix your parts, and it also shows that you don't need to do the same job on either side of the robot. In this case, you'll notice the job on the right, we're making quite a few parts, and on the left, we're really just making one at a time. Obviously, there's some space requirements for that, and in this job, the number of panels welded go into the next step of the process. But cycle time evaluation is really one of the things that we do up front to determine what cell makes the most sense. So how do you choose the right cell for your welding process? The first thing we do is we do a cycle time evaluation to not only to determine the payback, is it going to make sense? Am I going to be able to make 5 more of these a day than I can with a manual welder or not? But how should the cell be configured so that it is the most productive and it makes the most sense for my situation? How many parts should be fixtured in each station? In the video before, there were several on the right. Oftentimes, people will think, if I'm going to automate, I've got a certain amount of square foot that the robot can reach, I want to cram as many fixtures in there. And if that's 10 fixtures or 20 fixtures, and I can gang up those fixtures, that's what I want to do. When we look at it, it really makes sense to look at the welding time, how much time does it take to load the part versus how much time does it take to weld the part. And it may or may not be better to fixture up 20 parts at a time. If you can fixture up 20 and you're only welding, you get to the end of a batch and you only have 16 parts left, you might have an operator stand and watch the first 16 parts be welded and then hit the stop button at the end, so that you're not welding on empty fixtures and welding on your fixtures and ruining tooling. And if something does get bumped or out of position, you might have to reteach 20 times as many points as if you were only welding one part. So it doesn't always make sense. Oftentimes, it makes one part per station, even if the parts are very simple, can be much more productive. How many robots should be working in the cell? When we look at the time, studies, and we find out it takes 6 minutes to weld these parts and 2.5 minutes approximately to load, if that's the case, it probably makes sense to add an additional robot to the cell to bring our total cycle time down to 3 minutes with 2.5 minutes of load time. And the real benefit there, if you've got if you have the work to justify that, is for a relatively small amount of capital increase in the overall system price, you're doubling your productivity without using any more floor space or any more operator time. How should your parts be oriented? Should they be in a system where the parts can move, or is it something where the welds all need to be done vertically down? How are we going to reach the welds? Those things need to be looked at up front. Operator comfort and cell usability. I think operator comfort is probably the most overlooked thing in choosing the right welding cell for a particular application. The thing that you've got to figure out is, in addition to how much weld time and how much load time is it going to take, is what else is the operator going to be doing? Is the operator have tasks that he's going to be responsible for? Is he going to have to do inspection? Is he going to have to look at every weld? Is he going to have to do grinding? Is he going to have to tack parts before they go into the cell? Is he going to be responsible for bringing material to the cell and bringing finished parts away from the cell, or is other people going to do that? Those things can all be looked at and make sense within the overall productivity of the cell, but also, what the operator's comfort level is. We also look very closely at how long, at that time study again, if, for example, going back to the same example, if we had a part that took 6 minutes to weld and took, say, 5 minutes to load, people hate standing still. If you have to stand still, that's how they punish you when you're 4 years old. Stand in the corner, don't talk, don't move for a minute. You don't want to punish your operators every part that they make. When you get to the end of that cycle time, it may make more sense, rather than having a common load and unload point on the cell, to have separate stations that the operator walks to. It's less expensive for overall capital, but also it's much more comfortable for the operator to be walking and moving during productivity, and that keeps your productivity up. The other thing is if you have a part that only takes 20 seconds to weld and 15 seconds to load, if you've got an operator taking a part out of a station, putting a new part in, putting the other part in, hitting the clamp and hitting the go button, and immediately the other cell is ready to unload, it seems like it would be more taxing on an operator getting more parts out in a day, but because they're constantly moving and they're constantly doing things, they don't get as bored, the day goes faster, and that makes everybody happier. This is an actual kind of example that I did with our offline teaching software for a customer, essentially welding gussets to these L brackets. This was done. I put this together as a time study. The customer did not believe that a robot could weld the parts as fast as an operator, because they have one welder, one operator that is just a machine, and he can weld these parts so fast. In this case, an operator can be loading the parts on the left as the robot's welding on the right. No matter what, that's going to double your productivity. And actually, the smallest return on any kind of a cell like this that I've seen is about 2.7 times the productivity of what it was before. The other example that we show from this fixture, something that I talked about, is how are we going to orient the parts. In this case, rather than rotating the parts around to be able to do both sides, the operator is able to load the first part in, weld the let's say bottom of the part, flip it over, take a finished part out of the cell, flip that over to weld the top side of the part, and put a new part in. So we're using a modular tooling design where we're doing this in steps to help not only increase productivity, but keep costs down. And that helps keep the cycle time. We have plenty of time, whereas this ended up being about a 25-second cycle time. We had the operators only busy for about 20 seconds. So we had plenty of time for the operator to flip to do that extra motion. And that was able to benefit the customer overall. Workflow is important. We need to figure out how the parts are going to come into and out of the cell and who's responsible for that. We have to know where this cell is going to fit in our facility. And if you have concerns that a low ceiling height or a narrow wall or a small area, it's very common for us to take kind of existing designs and manipulate those so that they fit and work best within your available location within your facility. Is a single load or unload point best? I've talked about operator comfort there, and that varies from application to application, but that can also be dictated by the workflow. Maybe it makes a lot more sense for a part to be coming in from the left side and going out on the right side. That's something that we can do as well. Maybe we want a robot loading parts or picking parts in and out of a cell. There's a lot of things we can get pretty creative in ways to make things the most productive for you. Flexibility. One of the things that I see is common with business owners, entrepreneurs, is they're thinking, if I buy a robot, if I'm going to spend this 60 to 80 to 100, 150,000 for this cell, I want it to do everything that we can do. And if that means instead of spending, 120,000, I spend 150 to get the cell to be able to do everything we can do, that's what I want to do. That's what makes sense. What I typically do is when I go into a facility, I look at the various processes and projects that are going to be automated, try to figure out how much of the robot's time that's going to take. And if you have one job that's going to take 40% of a robot overall, another job that's going to take 10%, and you have 10 or 15 jobs that are 5% of a robot, that is a simple common robot, as in the video that I had just shown, it might make a lot more sense to get a simple cell to kind of walk before you run, learn what it is that you don't know about robotic welding, and get your organization comfortable with that on a simple, straightforward process that is really a solid 100% win, rather than trying to build a cell that's really complicated and flexible. Anything that's capable of doing everything probably can't do anything really well. So the other side of that is it's also not necessarily uncommon to look at a job that a robot is definitely the right thing for. The time savings, maybe bringing a part from TIG welding to robotic MIG welding, maybe we can get the same or better quality or less distortion. Maybe we're taking the time to do a job from 2 hours to 15 minutes. That's not necessarily uncommon. So if we do that, now maybe the parts that took 4 welders all day to do, the robot's only using about 20% of its capacity to do. In that case, maybe it does make sense to add in additional stations to do other jobs or other tasks. So that's something we look at very closely. The other thing that we look at is, do the parts need to be rotated, tilted, manipulated? Would we be better off to flip the parts manually, as in the video I showed? Or should we maybe use a 7-axis robot to be able to reduce the number and costs of positioners? This video shows a 6-axis robot on the left and a 7-axis robot on the right. The axis on the 7th axis is the one that's turning now. The guy that invented these for us actually calls it a back scratching robot, because it can reach anywhere on your back to scratch it. If you had an extra joint, it would make life a little more interesting that way. You can see, trying to weld around the base of this tower, the 6-axis robot can't really get around it. The only way to do it would be to rotate the tower. The 7-axis robot, you can see how far it could go with the 6-axis. When the 7th axis kicks out, not only can it reach back around the robot to be able to weld 360 degrees around the part, but it can go all the way 540 degrees while maintaining the appropriate torque angle. So it can add a lot of flexibility. Adding a 7-axis robot versus 2 positioners to turn the part might only be a third of the additional investment that it would be to add the 2 positioners. So it can be pretty dramatic cost savings. I'm going to turn things back over to Brent with our second poll question.
Okay, for poll question number 2, what is your top concern when considering robotic welding for your fabrication process? Our products and process mix is not right for automation. You're unsure how to integrate robots into our workflow and culture. Robots are too expensive, or robots are difficult to support. Give everybody about 30 seconds to answer.
Yeah.
Okay, last call. And let's look at the results. So it looks like the #1 response was our products and or process mix is not right for automation. So that's it's an interesting answer as far as the leader of the pack there. I think a lot of what Brian has been speaking on is how we can be very flexible in what we do as far as the robotic automation. And so I think with flexible tooling, a flexible system, even on short run volume parts, I believe that in most cases we can look at automating your process.
Yeah, and that's something. I'm sorry, and that's something that you know, it makes sense to have somebody come out and look at what you're doing that is good at this, that's good at automating your welding process, because there are things that you're probably not considering that a professional will be able to add a lot of value there. I think there are a lot of great people even within our organization that can come out and help you figure out what really makes sense. One of the questions, Brent, was the cost of a robotic cell, and it was second or third. It looked like in the order there. One of the things that's something that surprises me is that we sell cells that start out maybe at $60,000 and go up to above $1 million. Probably, I'd say 60% of the cells that I sell are less than $100,000, and 80% of them are probably less than $150,000 or $160,000. So a lot of people think robots are more expensive than they are. Is that something that you're seeing as well, Brent?
Yeah, especially, people first getting into robotics. One thing you got to consider is you're investing into your process and your production. So this robot system, when it hits the floor and starts welding parts, is immediately starting to pay back itself and make money. So you're not losing money like purchasing a car or something along those lines. You're actually investing into your business and increasing your profitability. So maybe that upfront cost looks a little daunting sometimes, but again, it will pay itself back pretty quickly and immediately start making money. And we offer, which Brian is familiar with, and we can provide, is some sort of cost analysis to give you an idea of a time frame for ROI or what your piece price may be. And that's something you can evaluate and compare against what your current costs are to really get a good feel for how quickly you're going to pay the system back and what your profits are going to be once you bring this online.
Yeah. Well, thanks, Brent. We'll get back to the presentation now.
All right.
So the next thing that can be kind of daunting is fixturing your parts. Who's going to design and build the weld fixtures? Am I going to need a different fixture for every part? Is the tooling and fixturing going to cost more than the robot, which can be the case sometimes? So who's best to build and design your tooling? Is it best for the cell manufacturer or the integrator to design your parts or design your fixturing or your tooling, or is that something that you can handle in-house with your current engineering and fabrication departments? Clearly you're making things, so that often is possible. How simple or complex does the tooling need to be? Just tacking or hard locations and pins and clamps at each weld to hold everything specifically in position? And I'll say, welding in general, we can handle a tolerance of about half of a wire, the wire diameter in MIG welding. So that means if we've got an 045 wire, we can handle 20, maybe 25 thousandths of an inch variation in joint location before the joint starts to wander. Varies depending on the size of the weld and the materials. So it's a good generic rule of thumb. So if you think you can hold your parts within 20 thousandths of an inch, then everything can get much more simple. There are simple fixture methods. There is a company, possibly multiple companies, that make inexpensive slot and tab tooling something that you can design yourself, you can go out and buy software for $8,000 to $10,000 that enables you to upload 3D models of your parts, tell it the thickness of the material you want to build the tool out of, tell it the type of clamps that you're going to build the tool out of, and it will spit back not only a design for the tooling, but actual programs for your laser cutter, plasma cutting table, water jet printer, to actually cut the parts along with instructions of how to put everything together like an erector set. So tooling doesn't have to be crazy difficult. There's also modular tooling, as the first video that I showed, the tooling on the left made out of modular weld tables. It's something your welders are very familiar with. There are a lot of off-the-shelf tool systems that can be put together in a very common, simple way, so you don't have to dedicate a fixture to a part forever. You can very quickly change out a few tools, put them in the right location, and then you're fixtured and ready to go for a job that you did last week or last month. There are also simple clamp and pin systems and spring clamps that can hold parts in the right location. And I say pin systems because when we're looking at tooling, we want to make sure that parts can go to the same place all the time. It makes more sense oftentimes to push to a button or to a pin that's going to locate the part, rather than pushing a part against something that's flat, where you could have dust or debris or even arc spatter or something building up between your tooling and the part that's going to cause your part not to be in the right location. And also, if you have a big part or a complex part, oftentimes the part can be pre-tacked by an operator in a jig so that everything's located properly, then presented to the robot for welding. You can do that instead of complex fixturing for large parts. A lot of times that eliminates that cost and really still can hit your productivity numbers well with a robot, because if you're not worrying about loading all the parts into a fixture, you're bringing the welder's time down to a fraction of what it was, and the robot is doing all the difficult work. Some examples, just some pictures of modular tooling on the left, the slot and tab designs that I'd mentioned in the top center, and on the right, just simple benchtop clamping, manual, and then pneumatic. Actually, it's hydraulic clamping on the parts below that with a little dial table. So, and as you can see in the middle, fixturing can get very, very complex, or it can be very simple. If you can't hold that 25 thousandths tolerance with your parts, or maybe you're bending a part and the bends vary, parts just aren't consistent, and you're afraid that's the issue why you can't robotically weld, there are times when that can be a problem. But there are also times when you can use the robot to, or where the robot can use joint sensing or tracking. The most common types are touch sensing and through the arc seam tracking. This doesn't require really expensive sensors. The touch sensing actually moves the wire to the part, touches it, finds it, and then adjusts for the variation from where the part should have been to where it is, and adjusts that weld or a series of welds. Through arc seam tracking, oftentimes is used in conjunction with touch sensing to find, so the touch sensing can find the front of the joint, and seam tracking weaves the torch across the joint and measures the changes in current during the weld, and has the robot actually follow that joint. So it can follow things real time. If things are a varying radius that can't be controlled real well, the robot can follow that. If it's a part that is distorting and moving, the robot can follow that. So that can be, those are the most common and have been around for the longest time. If that is not enough to do the job, or touch sensing, for example, slows down your cycle time to the point where it's not productive enough, there are vision or laser processes that are available as well. Laser touch sensing is very fast and accurate. You don't have to wait for a wire to come in and find where a part is. You can, as quick as you can take a picture, you can adjust the point or series of points, and you're welding. So it's very fast, very accurate. Laser seam tracking can track the joint for variation and distortion in all axes, not just variation in where the weld's wandering, but in all axes, and can maintain torch angles through those. And laser seam tracking can also monitor and adjust the gap to gap variations or part fit up variations with either weaving or adjusting welding parameters overall. I'll show some examples of that. First video is just a quick example of laser seam tracking. You'll note that as the torch progresses, it actually follows the contour of the part, keeping the torch nominal to the surface so that that torch angle is always correct. And also the torch angle itself, the push angle, is programmed into that's something that you program. That is maintained as well. You can't really see it from this view, but if we're asking for a 5-degree push angle or a 15-degree push angle, that's going to happen. With robots, it's real easy. If you have everything set up to a 15-degree torch push angle and you want to switch to a 10, there are ways to do that all at once. This video shows the adaptive fill or smart welding. This is what it looks like if you weld a part that you weren't expecting to have a gap, and there is a gap. The gap is about 80 thousandths of an inch. You can see the results can be pretty bad. You'll notice the sound right at the beginning. As soon as it starts welding, it kicks up. The laser senses that the gap is there, changes the welding parameters, and makes that weld on a gap surface. And you can see how that can be valuable. And that wasn't adding weaving or anything, just changing the process. In this case, an operator is actually going to clamp a 80 thousandths spacer in between these two 40 thousandths pieces of material, or actually the material is probably even thinner than that. You'll notice, and the parts were also clamped in at just any kind of angle. You can see they're not actually touching the tooling pins on the front of the part. So the laser finds the beginning of the weld, and you can actually hear it changing the pulsing parameters, changing the welding parameters as it's going through the gap to compensate for the changes real time and variation. So this can follow a gap, but it can also follow the part if it moves. It can do this in conjunction with following the part around. So you can see even with this, we were able to, the robot was able to get a good weld even across these variations up to 80 thousandths of an inch, which is pretty impressive. The next thing that you need to consider is who's going to program these robots we're going to get. We've decided that, we figured out what cell we're going to get. We figured out that there's benefits from them. Who's going to run these robots? Who's going to program them? The welder or an engineer is usually what it comes down to. It is, if you use a welder to program the robot, we can really teach anybody to program a robot in 4 days. It takes years to become a professional welder. Welders have to know if I was approaching this manually, where would I start welding? How would I access it with the torch? Welders have thought through that many, many times. So if you have an engineer that's never welded, they're not going to consider those things. Welders also going to consider, if I weld this part first, this is going to distort and pull in. So maybe I need to put a tack in, or maybe I need to make this weld first, then this weld. That's something that that welders do every day, every time that they look at a job. An engineer or a tech whiz kid's not necessarily going to think of that. They're going to look at the welds. They're probably going to approach them in order. We're going to do this weld, this weld, this weld all the way around the part, which is probably most likely to causing distortion and problems with the part. So if you have only an engineer that knows how to program the robot, you're going to be in situations where the welders are going to have some animosity towards the robot. And anytime an engineer is programming the robot, they're going to need a welder anyway to explain sequences, to explain torch angles, and to explain how the heat's going into the part. So you're always best to have a welder programming the robot. There are cases where it makes sense for an engineer to learn how to program the robot as well. That one of those is if that engineer is designing tooling or fixturing, it's good to understand how the robot and the parts work together. it's good to understand where, accessibility, how's the robot going to access? And those things come a lot faster if you actually do a little programming and work with the parts. And the other reason is offline teaching software. If you're going to use offline teaching software, and an engineer typically is going to be responsible for that. They're most used to working with CAD programs. You're going to be pulling in drawings to be able to do that. And an engineer just makes sense in that case. Advantages of offline programming is you can program your robot while it's still making parts. So you can also analyze whether your current robot can reach a new model of part. If you're making a change, you want to make sure you can reach everything. And in welding, torch angles are really critical. So you want to make sure you can reach it with the right torch angles. Their offline teaching software is great for estimating a cycle time. As I shown in the video earlier about the gussets on the angles, it can be instrumental in figuring out what the cycle time is going to be on a part. You can also take a program that you're already running, make changes to it, and see how that affects your cycle time without actually shutting down your production if you've got something where things are really tight. You can also analyze new fixture design or new parts, new tools before you even cut metal. So you're not wasting money on something, or you're building tooling and you find, if I move this clamp here, this is going to be a lot easier to access before you actually build the part or build the tool. You can test features that you're unsure of. If you're looking at a complex shift from maybe a right table to a left table or through multiple robots, you can test that out on offline teaching software, and you're not going to cause it to crash into the table or crash into a part or maybe another robot. In some cases, you can actually program parts faster with offline teaching software than you could otherwise. That's not always the case, but in some cases it is. And you have the ability to edit or troubleshoot remotely. So that's that can be advantageous as well. And this is just an example of a part reach study. We could figure out if we're going to need to rotate the part, how much to be able to get to all the parts. We can figure out cycle time, make sure nothing's going to be contacted. This is something we can do in-house before a system's purchased, or you can use on your own going forward. So the next thing, and one of the things that I'll say is really key to the success of a company bringing in robots is, one, are your welders going to be replaced by robots? Do your welders think they're going to be replaced by robots? It's really important to have a good relationship with your employees, and that's really key. It's not uncommon for me to come into a facility and I talk to an owner or an operations manager, and they tell me, okay, we're going to go look at these jobs. Don't tell anybody that you're here about robots. And I don't have any problem with that. There are times when that makes sense, for sure. But the key is your relationship with your employees is what's critical. If you don't have a good relationship with your employees and you bring a robot in and you have a welder or a welding manager running that robot, you're going to walk out on the floor and find the robot. You're going to find the robot sitting idle while somebody's welding 20 parts. And you're going to say, why aren't you doing that job on the robot? They're going to say, it was much faster just to do it manually. Well, it might be faster to do it manually that one time. Maybe if you actually put the program in, built the tool, oftentimes a simple fixture is simple, and your welders are pretty good at coming up with fixes like that. Programming a robot may, on a simple part, only take 5 to 15 to 20 minutes, a half hour, depending on the complexity of a simple part. That time spent up front the first time to be able then to maybe get 2, 3, 4, 5, 6 times as many parts out per minute or per hour, maybe that time is well spent right up front. But certainly the 5th or 10th or 300th time you do that job, the full benefits of the payback of the robot are going to be kicked in, and it's going to make sense. So if you don't have a good relationship with your employees, they can sabotage this big investment that you've brought in because they think they're going to lose their job. The reason they think they're going to lose their job more often than not is because of the news. How often do you see news that says 6 million jobs are going to be lost to robots this year? We've been hearing that every year. And until COVID recently, there were no people. There were no jobs. There were no employees to fill jobs. I don't know how hard it is for you to find and keep good welders, but I travel a big part of this country, and everywhere I go, it's a problem. People have problems finding and keeping good welders. Robots, if you have good communication with your welders, they're going to understand their value to your organization. They're going to understand that these robots are going to augment their production. And I will say it is very common for a job shop or a fab shop to get a robot, to start moving projects towards it, to figure out what things make sense and get it in the cell, getting the robot welding it, and filling up that robotic cell and adding another one or a fourth or an eighth robotic cell in relatively high mix, low volume fab shops. So that's not uncommon. Part of that is the welders tend to like it better in the long run because they're not doing real repetitive, boring jobs to the level they would be otherwise. They're able to go out and do things where their talents are more appreciated in your production. Or the other thing is when you find out that a part that was taking you $26 to make is now costing you $8 to make, complete with labor and materials. Now all of a sudden you can go out and be a little more aggressive, bidding the jobs where you know you're gonna have the highest productivity gains from your robot. You're going to be able to sell that through your customers and increase that portion of your volume. That makes your factory, your facility, more productive. You're making more parts, which is overall helping your welders. You can also reward your best welders by promoting them to programmers. We've already talked about welders are going to be the people programming the robots. Make those welders your champion. The biggest difference between companies that are very successful with robots and not very successful with robots is somebody needs to champion that cell. And the closer it is to the person running the cell, if it's the welders, that's better than if it's the engineers or the managers. If it's the engineers or the managers, it's better than if it's the owner of the company. The closer that champion of who's excited about that robot, who wants to get jobs into that robot, who's responsible for filling that robot with jobs. If you find a welder that can be enthusiastic about that, that enthusiasm spreads. That will make you very successful in the short and long run with robotics. And there are cases I've seen where welders can no longer climb around, and let's face it, the average age of a welder now is well into the 50s. At some point, it's hard to climb around and manhandle and maneuver around big parts all the time. It just wears on you, especially after the number of years that people have been welders. Robots can do that without problem. And you can reward those guys that would maybe no longer be able to weld for you by bringing them over, having them program robots, having them run robotic cells. In some cases, maybe it's a big part where you're going to be doing tacking and getting them into the cell. You're going to need a welder to do that. It enables you to keep your good employees around longer. So there are some real benefits. There can be real benefits there as well. I'm going to turn it back over to Brent for our final poll question.
All right, for poll question number 3. When do you think implementation of robotic welding should be considered by your organization? As soon as possible? Once business activity picks back up? Once things slow to the point where we have time to consider? Once our employees understand robots are not a threat? Or once we have the right support personnel identified? I'll give everybody about 30 seconds to answer. Okay, last call. Let's look at the results. So the leader in the pack here is as soon as possible. Our competition has already gained advantage. It looks like coming in at second is once we have the right support personnel identified. I think those both those answers are what I would have expected. Identifying the right people is always key, and training them up, and creating them as more of a value to your company is always going to be key in your success moving forward. And with the times we're living in today, I can see as soon as possible being a great answer to get the ball rolling now and start automating your welding process.
Yeah, and the next two that were, once business slows down or once business picks up again, that's those are things that I hear quite a bit, Brent, and it's interesting because if things are slow now and you're not adding a robot, when things pick up, is it going to be easier to do that? Is it going to be easier to put those into production? And if things are so busy now that you can't do it, that's probably when you need the robot the most. There is a lag time from the time the robot is ordered until it's implemented, and then unfortunately, even once the robot is in your facility, you may have a couple weeks or a month before you're really productive with that robot, until you really, especially for a first robot, for sure. So there is some lag times there, but typically it's never a good idea to wait to be more productive.
I can agree.
So,
all right, back to you, Brian.
Thanks, Brent. At this point, I want to kind of turn it over to the attendees, and I'd like to answer any questions that you might have. If you can use the chat feature to send those in, that would be fantastic.
Well, thanks, Brian, for a great presentation. Why we're getting our questions in here. It's definitely a lot to consider about automating your welding process. Let's go ahead and there's some questions here I'm going to go ahead and read off. Question number one, you have me convinced. I need to get going with robotic welding. Where do we start from here?
So the best thing to do is give us a call. My information is going to be attached to the presentation. We're going to send out a link to this presentation with some information. Reply to us, let us know, and we'll get the right expert to your facility to look at what you're doing and try to figure out the ways to best move things forward so you're not making any wrong steps.
Yep, and you can always get on our website too, daihen-usa.com, and there's a way to make contact with us through there also.
Absolutely.
All right, question number two. Thank you for the insightful webinar. How do you help customers deal? Hold on one second here, sorry.
How do we get better at webinars? That's the question.
Yeah, exactly. All right. I'm losing my pain here. All right, there we go. Okay. How do you help customers deal with the wire burn back situations?
So wire burn back is usually caused from a feeding issue. It can depend on a lot of things. In the OTC equipment, there are settings that actually condition, or at the end of a weld, will adjust the wire stick out, the ball at the end of the wire, control that so you get consistent starts, which keeps that from happening on a start. If the burn back is happening during the weld, the key things you want to look at is it's probably a restriction that's not letting the wire come out, or something that's binding it up. It might just be as simple as replacing a liner. It might be as simple as going to another position. Sometimes it could be if an arm is bent into a position where we have a steep bend in the conduit. A lot of times we may just be able to reposition or change the arm angles on the robot to make that more smooth. That may eliminate those issues. But best thing to do is with OTC, it's great because we have 24/7 technical support, that there's never a charge. You call in, talk to our tech support, within, they'll either transfer you to somebody immediately, or if it's after hours, somebody will call you back within a few minutes and they'll help you and walk you through that. But there can be various reasons that you have burn back. And I would suggest, if it's an ongoing problem that you've had issues, contact our service or support, or have one of us come out and take a look at your application. It's probably something simple that we can deal with.
Sounds good. Got a couple more here, Brian. I'll answer this one just real quickly. Are we going to share this presentation? Yes, we are. If you have joined and registered, everybody will receive a copy of this webinar, and so that will be sent out afterwards. And the final question, how do we justify a cell without full load for the system?
So that can happen a number of ways. And the key is you may not be able to. You may be able to. I have sold cells that are running for maybe an hour a day or less that have tremendous paybacks. So it really depends on what your goal is. I'm working on an application, working with a customer right now where 20% of the robot, they have one application where it's going to use about 20% of the cell, but the justification is there to buy the cell even if it's only running at 20%. With that customer, we're looking at adding some additional stations so that they can do other jobs that they weren't necessarily initially thinking about automating. And that's one way to do it. The other thing is that robotic cells can be pretty flexible in terms of what you're doing. Maybe you're looking at applications that are just MIG welding. Maybe we could add, say, a plasma cutting station to that cell to make it more flexible. We could maybe add TIG welding and MIG welding, or have it welding steel and aluminum. There are other things that we can do to the cells as well. And there are even cases where we can have the robot drop the welding torch, pick up a deburring tool, and deburr laser cut parts. So there are a lot of you have a lot of flexibility in what the cell can do. The best thing to do is look at the cycle times, figure out how much of the cell each of your applications is going to take, and then look at the payback. If the payback is there and you're only running the cell for 2 hours a day, it probably still makes sense. It can be a little frustrating to see a robot sitting in the corner not being used, but if you know that that's overall making you money and making things streamlined, that's great. Sorry, I'm losing my train of thought a little bit, but the other thing that you tend to find with a robotic cell is you figure out what you do best with it pretty quickly. Within the first few months, you're going to have a handle on what it really does best for you within your organization. It makes it much easier for you to go out and sell more jobs that are going to load your robot, because that's where that's where your costs just went from $50 a part to $10 a part. Now you can be a lot more competitive in bidding those, and you can get a lot more of that kind of work in. Do you have anything else to add to that, Brent?
Yeah, throughput's always the first thing to consider, but there's other reasons to add a robot system into your production, and that could be whether you want to do quality control, or whether you're looking for more aesthetics, or you're reducing repair or anything along those lines. So, it's not always just the throughput. There are other reasons and advantages of adding a robot into your production floor. And just because it doesn't necessarily use up 100% capacity, most likely you'll get it there at some point. But there are other factors that make sense to adding some robotic automation.
Yeah, and we can look at making the cell simpler or less expensive by taking out motion stages, making those things manual, things that can slow down the overall production of the cell, but make it where the payback makes a lot more sense for you. So there's a lot we can do in that area.
All right, well, Brian, great job today. We've came to the end of our time. So as a reminder, there'll be a survey here once we close out. Please complete that survey as your feedback is greatly appreciated. Everyone will also receive a follow-up email, including a recording of this presentation. And this concludes today's webinar presentation. Thanks again for joining us, and stay safe and have a good day. And thanks again, Brian. Good job.
Thanks.